Okay, in this demonstration video we're looking at our first example of free fall, which free fall is defined as the motion of an object under the force of gravitation only. So if you only have gravity as the only force acting on an object, you're talking about free fall. This realistic example isn't one where we actually have free fall because there are other forces at work, air resistance to name one. But this is going to be an example of a baseball being dropped from a relatively high height above the surface of the roof of my backyard shed, and it'll give us enough data to see what the acceleration due to gravity is. And we're just dropping an object here. So free fall is defined as when we have only gravity acting on the object. We talk about it with objects that could be falling or that could be thrown up into the air, or objects that are projected at an angle. All of those things we will cover with the assumption that gravity is the only force acting on it. Here in this video, I've recorded a video of myself standing, as you can see, on top of a ladder precariously in my backyard, and I'm going to drop a baseball, which is where this targeting reticle is focused right now. The camera's a little bit at an angle, so you see that the coordinate axes here are a little bit off, but that's okay. We're going to play the video, which we'll play in slow motion. This is taken at 60 frames per second, and we can see what will be plotted as a dot diagram of the ball, similar to the very first motion graph I made, talking about like oil droplets being dropped out of the bottom of a car at equal increments of time. So let's take a look. Release the ball, and it is now falling, clearly. Each of these red rectangular images is representing the position of the ball in every frame, and you see a little bit of a trail there. As time goes on, these rectangles get further and further apart from one another, squares actually, which indicates that our object is actually increasing in its velocity in the same direction. And there we go. Over on the right side we have a position. This is the y, or vertical position, measured in meters as a function of time in seconds, and we should recognize this graph. We're starting at a zero position at the very top, as you can see on the very top left of that graph. That zero position is when we're all the way back at the beginning of the video, and the ball is up in my hand, or it is right there. Okay, that's the zero position. So this is moving down, which we're calling the negative direction, and as it's moving down, we see we have a curvy graph. So it's not linear, it's not moving at a constant speed, it's speeding up. And as it's speeding up, it's increasing every interval of time. It's increasing the distance traveled vertically. So we have a nice curvy graph here that tells us we have accelerated motion, and gravity is the thing doing the accelerating here. So we're going to switch this graph over now to the velocity in the y, or vertical direction. As we go into the velocity component, the data isn't as clean, but for the most part it looks linear, which we talked about in our motion graphs. If we have a curvy position versus time graph, then we should have a linear velocity versus time graph, assuming that we have a constant or uniform acceleration, that's all we deal with in this class, is uniform or constant accelerations. Okay, so you take a look at our y direction velocity, so vertical velocity is in meters per second on the y-axis, and we have time again in seconds on the x-axis, and we have a negative slope indicating we're traveling in the negative direction. And you can see just by reading off the y-axis, we start at 0 meters per second at the very top left, and we end up with a final y velocity just as the baseball is hitting the ground of maybe around 7.5 meters per second in the downward or negative direction. If we want to find out the acceleration, just like we talked about with our motion graphs, all we have to do is analyze this velocity time graph. If we get the value of the slope, then the slope on the velocity time graph will be the acceleration. So we're going to go and analyze this graph of velocity in the y direction as a function of time. And there's the same graph that we have over on the right side is now in our main window. And we've fitted a trend line which is linear. That's what the line here means. And our fit equation is your standard y equals mx plus b, but it's written differently. It's written as what's on the y-axis is velocity in the y direction. So this is your y variable, velocity in the y direction, equals this parameter a is the slope. So this would normally be m, but there's our slope. So the slope of this graph is represented by the a parameter. T is what's on the x-axis. So this is y equals mx plus b. Right there. So the a parameter is our slope, the b parameter is our y-intercept. So you can see the a parameter, the slope, come over here, is negative. It's in the downward direction, and it has a value of about 9.798, and that's in meters per second squared. The slope is going to be the y stuff units divided by the x stuff units. Come back over here to the right side graph. Y units are meters per second, divided by x units, which are seconds, gives you meters per second, or meters per second squared. So the slope here, represented by the a parameter, is about, if we round it, 9.8 meters per second squared, which is the local gravitational acceleration on the surface of the Earth. So that's one way we can figure out what the acceleration due to gravity is. That value for the acceleration due to gravity is constant. It has a special symbol, little g, lowercase g, and so anytime you see the little g, that's we're talking about acceleration due to gravity, and it's 9.8 meters per second squared. Take a look at the video one more time because it's cool.